So let's start off with networking OSS layers and addresses. This chapter is kind of a quick recap because I believe everybody knows this. So it just quick go through those topics. Let's get started. So when we're talking about network, we have a lot of different types of networks. So just focusing on computer network. So computer networks is composed of three different parts: and devices, intermediary network devices, and medium. When it comes to end devices, there are some examples. Hosts, we can call them hosts or clients, servers. If you're using some of the audio and video conference devices, we call them terminals, and also surveillance camera, CCTV camera, and other intelligence devices that are using networking, like printers. So when we speaking of intermediary network devices, which is called network devices for short. For example, routers and switches and hubs, firewalls, load balancer, those are definitely network devices. But we've just, in this series, we're just focusing on the switches and the routers because if you look at firewalls and the load balancer, those are, they need very different knowledge. For example, when you want to learn load balancer, you need to have very very rich HTTP protocol knowledge or some kind of application delivery related topics. So when it comes to medium, just kind of media, like we're leveraging some of the physical stuff to connect with each other for like copper or twin twisted cable, and we also have optical fibers to connect with some of the network devices, and also have WLAN or Wi-Fi or wireless connection. Those are medium. So traditionally, as a networking engineer, we're just focusing on the this part. The internet work part, or just the intermediary network devices part. The interface between the network engineer and the host engineer, or some host engineer, is this cable, physical cable, or RG45 cable, or something like that. So that's our kind of like interface responsibility. But something has happened, and virtualization and containerization, like Kubernetes, have emerged. So we already use a virtualized network or containerized networks. So that means a lot of components have been deployed onto the host or onto the server, but they function as a network devices. So this kind of you can see the responsibility might change. So next time we talk about very important and fundamental thing, which is OSI layered model. So typically we have two models, OSI model and TCP model. TCP model was derived from Unix operation system because TCP IP stack is embedded into Unix 40 years ago or 50 years ago. And this is our standard-based model. You can see there are 7 layers. So in this series, we just focus on these 3, I think. Physical layer, we have different physical layers. For example, Ethernet is a kind of physical layer. Also have SONET, SDH, or HDLC for fifth series link. Also have WLAN or Wi-Fi is another physical link. Physical link is kind of something with electrical signals and or beats. It just transmits some of the beats to the destination. And data link is the second layer. It cares about MAC address or Ethernet, for example. In case there's Ethernet, so Ethernet has a MAC address. So MAC layer or RRC layer belong to the data link. And we also cover a network layer, which is IPv4, IPv6, or that's something that you're pretty familiar with. And when we look at TCP/IP model, just these 3 upper layer are combined and become a 1 layer, which is application layer. So for transport layer, they are the same. The transport layer, we mean TCP and the UDP sort of are doing some transportation and transport acknowledgement and flow control, those kind of things. So these are OSI models and the TCP/IP models. So when it comes to layered model, so when we're encountering some of the complicated problem, we try to separate them into different layers for the ease of troubleshooting or analysis. And that means that turns out we have to use encapsulation and decapsulation for individual layers. And for example, there's encapsulation function from the upper layer, from the top to the bottom. So let's say we have this computer just send out some of the email data. Email data might be are pretty large, so you just chop this large data will be chopped or sliced into the fixed length of chunks. Here is 3 chunks, and they go down to the transport layer, which is we call segment, and by adding the transport layer header, so we kind of like encapsulate this application data into transport layer structure. And likewise, when the packet goes down to the lower layer, they just add this corresponding header for this is an IP header. So we can see how encapsulation works here. So by just wrapping upper layer into the lower layer, this encapsulation. So decapsulation is reverse reverse operations. So it works from the bottom to top. So some bits or some bits comes in, and we just decapsulate the bits and just analyze them, and also just get rid of some of the header, and we just extract the real data and send it to the upper layer. And then in turn was sent to the application data will be sent to the very top, and so the customer can use this real data for their application. So this is a decapsulation. So from different individual layer, we have a particular term. For example, just be careful with the when we communicate those especially complicated networking design or networking deployment, you have to use appropriate term. For example, for data link layer, we call it a frame. For IP layer, or network layer, call it a packet. For transport layer, we call it a segment or datagram. Those kind of things. Just different layer has different particular term. So next up, we talk about a little bit about devices, because I think I believe everybody already know addresses. So from the data link, we have a MAC address, right? Because so for example, Ethernet. When we look at Ethernet is a multi-access medium or data link. That means that within one data link, we can deploy many devices. So a data link is a multi-access layer. So that means we try to differentiate specific device. We need addresses. For Ethernet, MAC address will be used. For network address, we have IP. Just differentiate different devices within this. In terms of this network layer, we also have transport. This differentiator, which is called a PCP port, a TCP port and UDP port, to differentiate different services or application. So addresses means those things. So when we take a close look at data link addresses, which is MAC address. So you can see how we use MAC address. So every network adapter has its own MAC address. So around the world. So as this guy just send out some of the packets to this server, so it just using this computer sneak, and the NAS hub will be the default gateway. The default gateway also had its own MAC address and also have this NIC network adapter. So every network adapter had its own MAC address. So it's kind of like here we have three data link, one data link, two data link, the second data link and third data links. Third data link. So every data link we have our own data link addresses. So that means if we try to achieve this target to send this packet to the destination, we need to change our MAC address from the data link point of view for specific data link. So from this data link, we change we use this green MAC address and MAC addresses for this second data link. We use this pair MAC addresses. So you can see from the frame point of view, the MAC address always changes, but IP address, source IP and destination IP within this communication does not change. Yeah, for layer 3, for IP, I just mentioned that if we, in terms of layer 3 point of view, which is IP layer, source IP and destination doesn't change, but the MAC address for different data link might change. So if we try to achieve this kind of target, we need to use a router to perform a routing operation between the data link, because there's a one data link, there's a second, there's the third. So we'll talk more about routing in the next chapter. So let's talk about the message delivery option. So let's say we already talked about communication. It's kind of like a one-to-one communication. So source send out the packet to this only one destination. It's a one-one relationship or one-one communication. But sometimes we need to do more, like one-to-many communication. There's only one sender, but the receiver might be more than one. This is called a multicast communication. So for multicast communication, in terms of different layer, we have different factor of addresses. Like we have a different MAC address, multicast MAC address. We have multicast IP address. In regard to the IP layer. And also have a broadcast communication relationship. This is a one-to-all communication style. So this is if the sender send out a broadcast, and all of the other devices will receive this broadcast frame or packets. So unicast also have MAC address, unicast address, and also have IP broadcast address in terms of different layer. IP addressing and subnetting. I think all of our guys just very familiar with IP address, but addressing and subnetting is also pretty important. It's a very, very essential tool for you to design a network or for your deployment of the networks. Because sometimes or most of the time, customers just give you a large space or a range of IP block. So you have to cut it into different, we call it subnetting. You have to subnet those large block into different IP subnets for your specific deployments and the design. So so that means you have to pretty familiar with network mask and IP prefix this kind of mappings, and also need to familiar with, for example, which one is a network address, which one is the first available host address, or which one is the last available host address, which one is a broadcast address. So those kind of questions, so you have to get an answer very quickly, and just in terms of your different design rules and some of the customer requests. For example, here we use 24, which is the simplest one. So you can see that we use this 192.168.1.0 as a network address, but the first available address will be 10.1, and the last will be 10.254, and this whole broadcast will be 10.255. So what about the /28, /27? So I think you just take some time to get a hand of it. Okay. Multicast starts with this 224. So if you look at 224, that means this is a multicast address. Multicast address, just give you a little bit action, or just a brief here. If the sender send out a multicast packet or multicast frame from Ethernet point of view, so just this switch, even we just send out only one copy of the frame, the switch will automatically replicate this frame to more frames and send it to the appropriate receiver. Like here, in this case, there are two receivers here. So one packet going out and two packets or two frames to the receivers. So let's talk about ARP protocol. And as I think everybody already know ARP protocol. ARP protocol is a protocol that map layer 2 address and layer 3 address. For example, ARP is protocol that maps MAC address on Ethernet and the IP address on network layer. So let's say here a HANA wants to talk to Jesse, but it only knows its IP address 10 down, which is 10.1.12. It doesn't, HANA did not know the Jesse's MAC address. But from Ethernet communication point of view, HANA has to have a corresponding or appropriate encapsulation for Ethernet frame. So HANA has to know Jesse's MAC address. How did it do that? They just say, shout out, hey everybody, just if you know this IP address, please tell me its corresponding MAC address. And Jesse just listen to this request and send out the response with this correct MAC address. So HANA knows this MAC address and doing the do the encapsulation and send out the Ethernet frame. So that's that is what ARP protocol is for, just the mapping protocol. So for different layer 2, for example, frame relay or ATM, they have different kind of like a mapping protocol.